Thank you, everyone, for joining today's webinar on contaminant removal from mining-influenced wastewater using permanganate oxidation. Presenter today is Lyndon Bierwick. I am our moderator, Dylan Kemmer. A couple quick housekeeping items before we get started. Everyone is in listen-only mode. If you have questions, we encourage you to submit those through the presentation using the question pane in the GoToWebinar panel. Please submit questions throughout the presentation, and we'll receive a report with the questions and your contact information, and then either follow up with you after the webinar, or if we have time at the end, we can do a question and answer session. We will be recording this, so that recording will be available upon request after the presentation. Lyndon Bierwick is a technical and field specialist with the CARES Technical Solutions Group. He has over 15 years of chemistry experience in both research and industrial sectors, including oil and gas production, environmental geochemistry, potable water treatment, and oil field specialty chemical sales, applications, and service. After completing a PhD in 2009, he worked as a full-time geochemist. He worked as a full-time research fellow with the Organic and Isotope Geochemistry Center in Curtin University in Western Australia. He was then employed as a production chemist with Baker Hughes, responsible for the on-site management and monitoring of chemical treatment program for Chevron's Australia oil and gas operations on Barrow Island, Western Australia. Lyndon has now been with CARES for over 4 years since moving to the US from Australia in 2018. And with that, I will hand it over to Lyndon for the presentation.
Thanks, Dylan. Let me go into slideshow here. Just making sure you can see the screen and hear me okay?
Yes, we can.
Excellent, thank you. So thanks, Dylan, and good afternoon, everyone. Today we're going to talk about contaminant removal from mining-influenced wastewater using permanganate oxidation. These are the main talking points that we'll address during the webinar. First, a little background on mining-influenced wastewater, and then the properties and reactions of permanganate that can assist in treating these types of waters. We'll then look at both laboratory and field data from several industry case studies and the key testing and results designed to address specific wastewater treatment goals. This will include the types and concentrations of contaminants, optimization of oxidant dose, the impact of pH, the order of chemical treatment, and the addition of coagulant and flocculant products. Finally, we'll highlight some of the key operational benefits observed for these particular applications. So there are numerous factors to consider for the treatment of the wastewater or processed water that is produced during mining operations. Some of these include water scarcity and the potential requirement for water reuse or recycling, the type and concentration of contaminants like heavy metals, the type of chemical and physical treatment strategies that are used, and the specifics of the effluent discharge, such as the discharge location, whether that may be city water or local water bodies, any specific permit requirements, and also toxicity testing. Chemical oxidants are often applied to precipitate soluble metals before the addition of coagulant and flocculant products for solid separation and water clarification downstream prior to discharge of the treated water. So what is permanganate? In chemistry terms, permanganate is a highly oxidized form of manganese, which is a transition metal similar to iron. Products are available in different physical forms and compositions. We have crystalline powders, which are concentrated but have a lower water solubility, but they're also available as diluted aqueous solutions, 20 to 40%, which can be more convenient to receive and feed. Permanganate solutions will be light pink to dark purple in color, depending on the concentration of the solution that we can see in the picture down here on the bottom right. Some of the common permanganate applications include pre-treatment of potable drinking water, treatment of municipal and industrial wastewater, soil remediation, odor control, oil field produced water treatment, and oxidation of organic contaminants. So there are many different commercial oxidizers available, so why use permanganate? One of the major benefits is that permanganate reactions are extremely fast, so it can be used where there's minimal reaction or retention time. Some of the classic reactions with inorganic contaminants that we've highlighted here include oxidation of soluble iron to insoluble iron oxide, the oxidation of soluble manganese to insoluble manganese oxides, the rapid oxidation of reduced sulfur compounds like hydrogen sulfide, and also the oxidation of pyrophoric iron sulfide. This is commonly used during refinery turnarounds and tank cleanings. So with that brief background covered, let's look at a case study that we've done extensive work on here at Caris and forms a major content of this particular webinar. This study focused on thallium removal from wastewater at a gold mining operation in South Carolina. Thallium is a highly toxic heavy metal that is soluble over a wide pH range. Leaching of thallium during processing of various mineral ores can often exceed discharge limits or regulations in mining water effluents. The Haley Gold Mine is located in Kershaw, South Carolina. In 2021, the operating company, Oceana Gold, approached Caris to replace their existing hypochlorite oxidation treatment with our Carisol C liquid permanganate product to try to help optimize their wastewater treatment process. Some of the issues that were encountered with the previous hypochlorite treatment included the potential generation of chlorine gas at low pH, inefficient removal of iron and manganese, which was contributing to significant fouling of their downstream microfiltration process, and also residual chlorine being present in the effluent discharge. So this excess chlorine often required the use of sodium bisulfite to dechlorinate the water prior to discharge to their outfall. So the key operational goals that we targeted here with the permanganate treatment included safe, efficient, and consistent thallium removal, which is one of the key parameters that is monitored for the mine's discharge permit. The efficient removal of other metals of concern like iron and manganese, improved performance and reduced maintenance and cleaning of the downstream filtration system. And also we looked at in situ process control and monitoring for parameters like permanganate residual, metal concentrations, and oxidation reduction potential. So with these operational goals in mind, our lab studies were focused on 4 main areas. The impact of varying permanganate doses on thallium, iron, and manganese removal, the impact of the order of chemical addition on metals removal performance, the impact on performance with and without ferric chloride coagulant, and finally, analytical methods for in situ monitoring of permanganate residuals. The lab jar testing procedure that we used was designed to closely mimic the wastewater treatment process at the mine and at the time. The basic schematic is shown here. Water from the waste pond A19 here is dosed with permanganate on its way to the reaction tank. Hydrated lime is added for pH adjustment, followed by ferric chloride coagulant, and flocculant. The flocculant is then added to flock and drop the solids in a multi-flow clarifier. In the jar test experiments, both filtered and unfiltered aliquots of the supernatant that we collected in the jars here were collected for further analysis of total and dissolved metals after the solids had settled. So let's look at some of the key data from this study. The first data set here shows the Carousel C dose using for total thallium removal. The plant operates at a pH of around 9. So if we focus just on the blue data points here, we can see a clear linear response for thallium removal. And the optimized dose was around 35 ppm. This dose was able to reduce thallium to the target level of less than 0.2 micrograms per litre or parts per billion. We also wanted to look at the impact of pH and whether we could achieve more efficient thallium removal using a lower Carousel dose at higher pH. So the brown data points here show that there's actually no significant difference in thallium removal efficiency by increasing the pH from 9 to 9.5. The next data set here shows an evaluation of the impact of the order of chemical addition on thallium removal. So again, the data in blue shows thallium removal using the current strategy of applying oxidant first, then adjusting to pH 9 with lime. The data in brown, on the other hand, shows thallium removal by adjusting the pH before adding the oxidant. So we saw an approximately 20% reduction in the Carousel dose required to achieve that target thallium level by adjusting the pH first. Again, the aim here was to try to optimize the process and provide the plant with options for potentially reducing their chemical usage and the overall cost of treatment. So with thallium removal being one of the key process treatment goals, this slide provides a bit of an overview of the removal mechanisms taking place. I won't go into too much detail, but what we know is that permanganate oxidizes dissolved thallium as well as other major metals components like iron and manganese. The key reactions are listed in the equations 1 to 3 here. The insoluble precipitates that form from these metals can then be removed by coagulation and flocculation. The manganese oxide precipitates are also generated during the reaction, and these components also facilitate thallium, iron, and manganese removal by a combination of precipitation, co-precipitation, and adsorption at alkaline pH levels. So with these mechanisms in mind, we know that permanganate will also react with other metal components in the wastewater, and these are typically present at much higher levels than what you would see for thallium. The permanganate or oxidant demand is mainly consumed by these more highly concentrated components like dissolved iron and manganese that I've described. These metals also cause significant fouling of the microfiltration units and can reduce the overall throughput volume in the plant. So the data here shows a clear dose response like we saw for thallium, this time for iron and manganese removal. At the optimal 35 ppm dose that we observed for thallium removal, we can see that iron is also below detection limits and manganese levels are reduced below 1 ppm or milligrams per litre. Permanganate is much faster than hypochlorite, particularly for manganese oxidation, and doesn't require the excessive feed rates. So the flow-on effects of this mean reduced filter fouling, increased plant throughput, and reduction in chemical costs associated with neutralizing that residual chlorine present in the effluent. So this next slide highlights the permanganate half of the oxidation reaction. The colors here are deliberate. When permanganate is dissolved in water, the solution has that distinctive pink to purple color that I showed previously. The precipitated manganese dioxide byproduct of the oxidation reaction is actually brown in color. This MnO2 or manganese dioxide is actually a very useful flocculant material that can play an important role in water and wastewater treatment. It can act as a coagulant aid or seed material that interacts with inorganic coagulants and polymers. It can help adsorb other charged impurities such as charged ions and some organics. and it also provides an active surface for the oxidation of sulfides by dissolved oxygen. So we wanted to look more closely at the potential advantages of the manganese dioxide reaction product, specifically for the Oceana Gold system. The data here shows the impact of adding ferric chloride coagulant on total thallium removal. On the left plot, we can see there's really no significant difference in performance with or without coagulant, effectively meaning this chemical can be eliminated from the treatment strategy. We also wanted to look at thallium removal in response to different influent water characteristics. So the main concern in this case is that with low dissolved iron concentrations in the influent, there may not be enough precipitated material after the oxidation to achieve sufficient solid settling during clarification. The plot on the right here shows that this actually isn't the case. Effective thallium removal was achieved with both high and low incoming iron levels, again, without the need to add coagulant. We've seen similar benefits for manganese dioxide acting as an in situ coagulation aid in oil field produced water applications using permanganate as well. Another important consideration for process control is to make sure that we don't overfeed the permanganate and carry a residual to the discharge point. This can potentially affect downstream conditions such as whole effluent toxicity testing, and this was an issue with the previous treatment using hypochlorite. We looked at several methods to track permanganate residual in the process, including UV-vis testing for a direct read of that characteristic pink color, HARC DPD free chlorine testing, which also reacts to the pink coloration, carrier test amperometric cell testing, and also oxidation reduction potential testing. The changing makeup of the influent process water meant that the baseline readings for both ORP and the carrier test analyzer weren't stable at 0 millivolts, so when no permanganate was present. So these were eliminated as online monitoring options. However, both the UV-vis and the DPD testing showed a stable baseline and an immediate response when permanganate was present in excess levels. The DPD online analyzers are readily available and easy to use, so this method makes a good process control to ensure no overfeed of permanganate during the treatment process. The plant at Oceana Gold, or at the Haley Gold Mine, continues to carry out spot tests several times a day using this particular approach. So to summarize the major findings from these particular lab studies, thallium removal increases with carousel seed dose, along with iron and manganese removal. Thallium removal efficiency can be increased by using pH adjustment with lime before adding the oxidant. The standard ferric chloride coagulant addition can be eliminated from the treatment process because the manganese dioxide byproduct provides an excellent in situ coagulation aid. And UV-vis or HARC DPD methods to evaluate permanganate overfeed are consistent and accurate and largely eliminate the need to remove excess oxidant with sodium bisulfite that was previously used or previously required using treatment with sodium hypochlorite. Some of the key operational benefits that the plant has observed since implementing permanganate treatment include increased thallium removal to less than the goal of 0.2 micrograms per litre, and that's despite influent thallium concentrations actually increasing. This has allowed greater operational flexibility whilst also maintaining comfortably below their permitted levels. The cleaning frequency for the microfiltration unit was reduced by 75% due to improved removal of those typical filter foulants, iron and manganese. And a flow on from this was that the wastewater plant was able to significantly increase their overall throughput and discharge volume. Here, so after implementing permanganate treatment in April 2021, the total discharge volume almost doubled, in April and May compared to March in the previous month. So we'll move on now to a second case study based on work performed at a metal smelting plant in the Midwest. This also involves thallium removal along with other heavy metals, lead and cadmium. I'm sure most people are aware of the issues with lead toxicity and lead exposure through lead mining and smelting, battery manufacturing, disposal and recycling, and you know, lead exposure is a global concern. Cadmium is probably a little less well known, but it is also a toxic and environmental hazard. Human exposure to cadmium can occur through fossil fuel combustion, phosphate fertilizers, natural sources, iron and steel production, cement production, and municipal solid waste incineration. Jar test studies at this plant were performed in the smelting plant to look at thallium, lead, and cadmium removal compared with their current treatment strategy, which was sodium sulfide. The experimental procedure is again similar to what we described before: oxidation and pH adjustment, followed by coagulant and polymer addition for solids settling and removal. The concentrations of each metal at the time of sampling were around 94 parts per billion or micrograms per litre total lead, 19 micrograms per litre total cadmium, and 20 micrograms per litre total thallium. The treatment goal here for the plant is to maintain monthly effluent discharge below 6.3 micrograms per litre thallium, 1.1 micrograms per litre cadmium, and 7.9 micrograms per litre for lead. The graph here shows the percentage removal of each metal at different doses of permanganate. The solid lines up the top here are for show the percent removal using the current chemical treatment and dose, which is around 50 ppm of sodium sulfide. But we can see in the dashed lines that permanganate achieves well over 90% removal for all three metals, and in particular clearly achieves much higher removal of thallium in the blue lines here. Optimizing the dose during the actual plant application showed removal of each metal contaminant well below the required discharge limits. This was actually achieved at around 100 times lower dose than the incumbent chemical treatment using sodium sulfide. And of course, a nice flow and effect of this is that the health and safety concerns around the use of sodium sulfide were eliminated. So we'll move on now and look more closely at iron and manganese removal. These metals don't pose a specific toxicity risk, but they do have issues in potable water treatment, such as scaling of pipe work, fouling of filtration equipment, and also aesthetic problems like taste, odor, and color in the drinking water delivered to customer homes. In terms of mining treatment, one of the major issues is in acid mine drainage. Surface and deep shaft coal mining operations have to meet EPA standards for the amount of acid, iron, and manganese in drainage waters. So I touched on this previously, but iron and manganese removal is really the bread and butter for permanganate treatment. Key treatment targets and advantages include the rapid oxidation of dissolved iron and manganese, no need for pH adjustment if it isn't required, although pH adjustment prior to permanganate addition can be more cost effective. I'll highlight this a little later again. We can also see enhanced solid liquid settling in holding ponds prior to discharge. The improved effectiveness of the coagulation process also results in better filter run-in times. And permanganate also doesn't form potentially toxic chlorinated organics, which can find their way into drinking water. So let's look at a third case study now, this time from a coal mine in Ohio. This was a 203-acre surface coal mine that was exceeding the NPDES permit for total manganese at 2 milligrams per litre. The problem area at pit number 4 contained runoff and leachate material metals with manganese in the range 4 to 15 milligrams per litre and iron in the range 1 to 76 milligrams per litre. So the chemical application strategy here was actually very simple due to the fact that it was a remote location with no power available. So we simply gravity fed Carousel into the runoff stream, and the chemical dose was adjusted manually based on oxidation rate and stream flow. The color change for the oxidation rate, again, as I highlighted before, was that change from the purple permanganate iron to the brown manganese dioxide reaction product. The data here shows the outfall monitoring data over a 6-month period. So the total manganese concentration was held consistently below the discharge limit of 2 milligrams per litre, and the 6-month average was 0.81 milligrams. And the total flow and run times were also maintained within the operational requirements after implementing the permanganate treatment. This is a second acid mine drainage case study from a coal mining operation in this time in West Virginia. The challenge for this site was again to reduce high iron and manganese levels in the wastewater. Drainage water samples were collected and showed an initial pH of 3.9, iron at 45 milligrams per litre, and manganese at around 19 milligrams per litre. The facility was required to reduce specifically manganese levels to less than 1 milligram per litre. So after the pH was adjusted to 7 or above, even up to 8 or 9, most of the iron was precipitated, and the Carousel permanganate was able to significantly lower the manganese concentration. A Carousel dosage of just 10 milligrams per litre at a pH of 7 was able to reduce iron to 0.35 milligrams per litre and manganese to 0.75 milligrams per litre. So well below that 2 ppm target. We've seen very similar results again for removal of these metals at another coal mining facility in Kentucky, again using pH adjustment first, followed by permanganate oxidation. That pH adjustment, and I touched on this earlier, is important for a few reasons. It raises the drainage pH to within EPA guidelines, which is typically between 6 and 9. The iron precipitates in the wastewater as iron hydroxides, which can then be removed by coagulation and flocculation. And it also reduces the permanganate demand or oxidant demand and treatment costs by removing some of the manganese just simply through pH adjustment. Our final case study here looks at this time looks at arsenic removal from a green sand filtration operation. Arsenic is particularly potent and occurs in many minerals, usually in combination with sulfur and metals. The main sources of human exposure include volcanic ash, weathering of minerals and ores, mineralized groundwater, and inhalation of atmospheric gases and dust. The advantages of using permanganate for arsenic removal include rapid oxidation of arsenic to very low levels, while also oxidizing iron and manganese, like we've seen with thallium. Manganese dioxide can absorb arsenic 5, as we discussed previously for some of the other key metals of concern. The iron oxidized by permanganate can also absorb arsenic, meaning the addition of those iron coagulants is often not necessary. And there is also no formation of disinfection byproducts in waters that may be laden with organics. So the challenge for this site in Saskatchewan was to lower arsenic from 125 parts per billion to a goal of less than 5 parts per billion. The solution was to operate the green sand filter in continuous regeneration mode, whilst adding our Carox potassium permanganate, which is the solid form of our permanganate products. The results were very effective. They showed 96% removal of arsenic from 125 parts per billion down to 5 parts per billion. And again, iron and manganese were also reduced to very low ppb levels without the need for additional iron coagulation. So just to briefly summarize the key takeaways from this presentation, permanganate is a powerful oxidizer commonly used in the water treatment industry worldwide. It's safe and easy to handle. It offers a rapid and effective treatment alternative to other common oxidizers. We can target a variety of key metal contaminants, including iron, manganese, thallium, cadmium, lead, arsenic, among others, as well as organic contaminants and sulfide-containing compounds. The reaction provides an excellent in situ coagulation aid for solids removal and clarification. This MnO2 that we produce can also reduce the required doses of those polymer and flocculant chemicals, helping to reduce the overall cost of treatment. It can also provide a more consistent treatment efficiency and performance for incoming water composition that can be quite variable, and can also help overcome effluent toxicity issues encountered with other oxidizers. So hopefully this presentation has demonstrated our technical expertise to help evaluate and optimize performance in the treatment of mining influenced wastewaters. Caris has been a world leader in the production of permanganate oxidants for over 100 years. And in addition to our permanganate and other oxidation product blends, we also provide a variety of coagulants, polymers, and catalyst technologies. We have a dedicated mining lab for analytical testing, consultation questions, and also performing treatability and feasibility studies. And finally, as part of our key technical support, which is mainly my role, we can provide extensive field application services, including on-site testing, treatment assistance, the design and installation of chemical feed systems, and the use of our online analytical equipment. So thank you everyone for your time today, and Dylan and I are of course happy to answer any questions that you may have. Dylan.
Thank you, Lyndon. We did have a couple questions come in, so there's some overlap from them. So I'll start with I'll probably combine some of these just to make it a little bit easier. So just to remind everyone, we will have this recording available. Additionally, if you're interested in the slides, we can provide those upon request. So feel free to email Lyndon at the email on there, or our sales and marketing email that's also listed, and we can definitely provide you with the slides. If you want to reach out to Lyndon or myself, feel free to use those links to talk to us about mining or any other applications. So questions for the presentation. The feed rates listed in some of the early slides for potassium permanganate or sodium permanganate, are those as active product, or are those as permanganate, or as like sodium permanganate or potassium permanganate? I know later on in the presentation you had listed as sodium permanganate, but early on,
yes,
there were some early slides.
Yeah, no, typically the feed rates that we list, and again when we're communicating with customers, will be as a total product. So not as active ingredient, just as the total product as you would feed it, whether that be a 20% solution or a 40% solution, or a made down solution of the solid permanganate, it will be as total product. So yeah, not as active ingredient.
Okay, thank you. And then in the first case study, were there solids in the solution prior to addition of permanganate? If so, how much contaminant? Oh, go ahead.
Sorry, no, there isn't, because this is the Oceana Gold study. No, the pH there is very low. It's around 2. So pretty much all the solids present in those in that influent water are dissolved. pH adjustment will help drop out some of those solids, and then the permanganate oxidation will help precipitate more of the solids at alkaline pH.
All right, thank you. And then it looks like we'll give people another second to submit any questions. Otherwise, it looks like we're wrapped up. So I appreciate everyone making the time today and joining us for our webinar on mining. Like I said, if you have any questions, feel free to reach out to Lyndon or myself using the contact information on the screen. Thank you, everyone.
Thank you, everyone.